Well, students, in the last class, we have started discussing on LU factorization methods. In this, we have introduced two methods. One is called the do-little factorization method, and another one is the fruit factorization method. Today, we will continue our discussion on Cholesky's factorization method. Let us first define what is meant by Cholesky's factorization. A matrix A is said to have a Cholesky's factorization if there exists a lower triangular matrix L such that A can be written as L into L transpose. Remember, L transpose will become a upper triangular matrix if L is a lower triangular matrix. Therefore, you again have A as a product of the lower triangular matrix L and the upper triangular matrix L transpose. So Cholesky's factorization is basically a LU factorization. Before getting into the construction of Cholesky's factorization, we have to recall certain concepts from linear algebra. First thing you can see that A should basically be a symmetric matrix in order to have Cholesky's factorization. I'm sure all of you must be familiar with symmetric matrices. Another property that one needs to impose is the positive definiteness of a matrix. Again, I'm sure that you would have covered this in your linear algebra course, but we will just recall what is meant by positive definiteness of a matrix. A symmetric matrix A is said to be positive definite if X transpose AX is greater than 0 for every non-zero vector X. Of course, if I give you a matrix A and ask you to check whether it is a positive definite matrix or not, you will have to first check that A is a symmetric matrix. And second thing is, you have to check this condition also, which often may not be possible practically. Therefore, there are some convenient equivalent conditions for a matrix to be positive definite. Let us recall these equivalent conditions. We'll omit the discussion on the proof of this lemma. You are given a symmetric n cross n matrix A, then the following three statements are equivalent. The first one is the matrix is positive definite. The second condition is that all the principal minors of the matrix A are positive. It means a given matrix A is positive definite if and only if all its principal minors are positive. If you recall, in the last class, we have introduced the notion of principal minors. You may go back and recall that and come back and continue this. And another equivalent condition is the matrix is positive definite if and only if all its eigenvalues are positive. So these two conditions perhaps can be easily checked rather than directly checking the definition. And also they are useful in proving certain results. With this in mind, let us go to state the theorem that gives us the existence and uniqueness of the Cholesky's factorization. And the proof of this theorem will also guide us how to construct the Cholesky's factorization. The theorem says that you are given a n cross n matrix which is symmetric and positive definite, then you can get a unique Cholesky's factorization with all the diagonal elements of the lower triangular matrix as positive. Remember, this is very important. If you impose this condition, then only you will get unique factorization. Otherwise, you may get another factorization which will not satisfy this condition. Okay. So if you fix the sign of the diagonals, then you get a unique L such that A is equal to L into L transpose. Okay, let us see how to prove this theorem. As I told you, the proof is constructive. Therefore, once you understand the proof, you will also get the procedure to construct the Cholesky's factorization. Okay, let us see how to prove this theorem. The theorem proof is by induction. This means first you have to consider the case when n is equal to 1. Let A be an 1 cross 1 matrix where A is strictly greater than 0. Why it is? Because A is positive definite. Therefore, small a should be strictly greater than 0. Then we can always define L is equal to the 1 cross 1 matrix root A. Then you can see that A can be written as L into L transpose. It's very trivial. Now assume that the result is true for any K cross K symmetric and positive definite matrix. And we have to prove the result for a K plus 1 cross K plus 1 symmetric and positive definite matrix. Note that A can be written as A is equal to AK, that is the K cross K matrix. So once you have K cross K matrix, then you are left out with one column, right, and one row here. And remember, since A is symmetric, this column is the same as the row as well. Let's denote this column by the vector A, then this side it should be vector A transpose. That is, if you write A as a column vector, then A transpose is the row vector. So let's take it as K cross 1 matrix, and this is your 1 cross K matrix, right? And they both have their last component as, say, A, K plus 1, K plus 1. So that is the matrix A. Now, what is the advantage of writing our matrix A in this form? Well, you can see that the matrix AK is a symmetric and positive definite. How can you see this? Well, this is not very difficult because A is symmetric and positive definite. Therefore, all its principal minus are positive, right? That is the equivalent condition we have stated in the above lemma. Now, once all its principal minus are positive, it means AK will also have all its principal minus are positive, right? Because A is given like this, and AK is just obtained by removing one column and one row. So we have taken this as the AK, right? So therefore, if you again remove one more column and one more row, you get another submatrix whose determinant is also positive, and you go like this, removing one row, one column in the backwards. All those submatrices will have positive determinant. That is what is meant by all the principal minus are positive. If A has that property, well, AK will also have that property. Therefore, it is positive definite. Obviously, it is symmetric because basically you got AK from A by removing the last row and last column, right? And A is symmetric, therefore AK should also be symmetric. So once you have this K cross K matrix, which is symmetric and positive definite, then you can use your assumption that you made for the induction method. It means we have assumed the result for any symmetric and positive definite matrix whose dimension is K. Therefore, you have Cholesky's factorization for AK as per our induction hypothesis. So we can assume that there exists a lower triangular matrix such that A can be written as the product of the lower triangular matrix into the transpose of that matrix, right? Now let us propose a L given by LK, which is coming from your Cholesky's factorization of AK, and then put everybody in the last column as zeros. So that's a zero column vector. Well, remember, L is not symmetric. It is lower triangular matrix. That is why we have taken this full column as zero. It's not symmetric. Therefore, don't put zero here. Rather, you put some row vector denoted by L, which is 1 cross K matrix. It has one row and K columns. And the last one should be L K plus 1, K plus 1. Right? So because it should be a K plus 1 cross K plus 1 matrix. It should go and define your A. Remember, you want to show now that A is equal to L into L transpose. It means what we want to do is we want to propose our L like that and to show that this is precisely our L which is going to work in our Cholesky's factorization of A, where this is just a real number. It means what? We have to show that our matrix A, which we have written as AK, then A, which is a column vector, and the same vector will come as a transpose here, which is the row vector because of the symmetric property of A. And then you have AK plus 1, AK plus 1, right? So that is your A, and the other side is L into L transpose, that is given by LK 0 column vector and L row vector, therefore LT, and the last element LK plus 1, K plus 1. And its transpose will be LK transpose, and this row vector will now become column vector. Therefore, I will not put transpose because by vector I always mean column vector. And then this 0 column vector will come here as the row vector, and then we have L K plus 1, K plus 1, right? So that is your L transpose. Now you see, you take this and multiply with this to get LK into L, that's a column vector on one side. Its corresponding, the left hand side is A, right? So therefore it will be the column vector A. We know A because we are given capital A, but we do not know L. Remember, we are given this matrix LK because we have already constructed the Cholesky's factorization for AK. Therefore, we know LK. What we don't know is this vector L and this real number LK plus 1 and LK plus. So these are unknown quantities for us, and we are trying to find these unknown quantities. Now, for that, we have just expanded what we want, that is A equal to L into L transpose, and we have multiplied the block L with the last column, and that gives us LK into L, and the corresponding left hand side we will have the last column other than the last, this AK plus 1, AK plus 1. You can just see it by writing, say, 3 cross 3 matrix. You will get a clear idea of why it is coming. And that gives us an upper triangular system. You can see that LK is an upper triangular matrix, and L vector, which is a column vector, which is unknown to us, we have to find that, is equal to the column vector A, which is known to us. So this defines a lower triangular matrix. A forward substitution can give us the column vector L, provided LK is invertible. Just think, is LK always invertible? Well, yes, because your LK is coming from your AK through Cholesky's factorization. Therefore, you have AK equal to LK into LK transpose. Look, AK is positive definite. Positive definite means all its eigenvalues are positive. It means AK is an invertible matrix, and AK inverse equal to LK transpose inverse times LK inverse. Therefore, AK inverse exists implies LK inverse also exists. And that is a guarantee that LK is an invertible matrix. So you can always solve this upper triangular matrix by the direct forward substitution process and get the unknown vector L. Now what remains to find is only this last element LK plus 1, K plus 1. Let us see how to find this. Now what we will do is we will multiply the last row of L with the last column of L transpose. That gives us L transpose into L, right? That is this into this plus LK plus 1, K plus 1 into LK plus 1, LK plus 1, that is LK plus 1, LK plus 1 square, and that should be equal to, see, last row and last column should be equal to this quantity, right? So therefore, on the right hand side, you should have AK plus 1, K plus 1, right? So from here, we can get the unknown LK plus 1, LK plus 1 square as AK plus 1, K plus 1 minus L transpose L. And you can see that you have already found L, therefore L transpose L can be obtained, and AK plus 1, AK plus 1 is given as a part of your matrix A itself. Therefore, we can obtain LK plus 1, LK plus 1 square, and from there we can take the square root to get the number LK plus 1, K plus 1. But here there is a problem, that what is the guarantee that this is positive? So there is a big question mark here. If it is not positive, then we will face problem in taking the square root of that number to get LK plus 1, K plus 1. But you can show that this quantity is positive. How? You take determinant on both sides of this equation. We will get determinant of A is equal to determinant of L square, right? And that can be written as, you see, this complete column is 0. Therefore, you can write this as determinant of LK square into LK plus 1, K plus 1 square, right? Because this is determinant of L, the whole square. Therefore, we are having LK plus 1, LK plus 1 square. Now you can see that determinant of A is the product of all the eigenvalues of A. That's an elementary property from our linear algebra course. And our previous lemma says that A is symmetric and positive definite if and only if all its eigenvalues are positive. Therefore, the right hand side is positive. And here you have some real number square. Therefore, this is surely positive. It means LK plus 1, LK plus 1 square should be positive, and that will give you guarantee that this is positive, although it is written in this form, which gives us ambiguity that whether it is positive or not, right? But this point of view clearly says that L square has to be positive, and therefore this anyway has to be positive. Well, what we want is that this should be a positive quantity, because we are going to take square root on this only. So surely the number which comes out of this expression is going to be positive. Okay, this is what is given through this equation, and that makes us to complete the construction of L. Okay, again, what we did is we have assumed that any matrix with dimension K, which is symmetric and positive definite, has Cholesky's factorization. And then we wrote our given matrix A, which is a K plus 1 cross K plus 1 matrix in this form. And by our induction hypothesis, we have obtained the Cholesky's factorization for AK, through which we got LK. And then we proposed our required L in this form, where this vector L transpose and this number LK plus 1, LK plus 1 are to be obtained, whereas this capital LK is known from our previous Cholesky factorization. The vector L is obtained by the forward substitution process of this upper triangular matrix. And the real number LK plus 1, LK plus 1 is obtained by using this relation, and its expression is given like this. And we have made sure that the right hand side, which is the difference between 2 points, finally happens to be a positive number. Therefore, LK plus 1, LK plus 1 will be a real number for us. And that completes the construction of L. Well, when you are taking LK plus 1, LK plus 1, you see it is coming from square. Therefore, this will be plus or minus root of AK plus 1, K plus 1 minus L transpose L, right? So, you have two possibilities to define L depending on whether you take the positive of this or negative of, right? But if you fix the sign to be positive or equivalently negative, then you can see that this construction gives you a unique Cholesky's factorization. The proof is now complete by induction. Now coming to the construction of Cholesky's factorization, if I give you a symmetric positive definite matrix, how to find the Cholesky's factorization is the question. Well, from the above proof, we can in fact construct the Cholesky's factorization, but it is not very apparent because we made it in the form of induction hypothesis and proved the theorem. Let me summarize it in the form of a nice constructive way so that it can be used as a method to obtain the Cholesky's factorization. So we are given a matrix A which is equal to say A11, A12 and so on, A1n, A21, A22 and so on, A2n. Like that you have AN1, AN2 and so on, ANN. Now we have to find the Cholesky's factorization. Assume that A is symmetric and positive definite, because we know that if A is symmetric and positive definite, we can construct the Cholesky's factorization. However, sometime I may give a system for which the coefficient matrix is not symmetric and positive definite, in which case you can do a little modification. Like for instance, if I give you AX is equal to B, where A is not symmetric and positive definite, but ask you to do Cholesky's factorization, then what you can do is you can write the same system as A transpose AX equal to A transpose B, right? Then A transpose A you can take as B, and that will happen to be a symmetric and positive definite matrix. So you should keep that in mind. Now let us go to see how to construct this Cholesky's factorization for a given matrix A if A is symmetric and positive definite. What you do is you take A1 is equal to A11, and from here you define L1 as root A11, right? So once you have this, then write L2 is equal to L1, 0, L21, L22, and demand A2, which is actually equal to A11, A12, that is the principal submatrix of order 2 as L2, L2 transpose, and from here you can find L21 and L22. Once you have this, you know what is L2, then you go to define L3, which is equal to L2, that is a 2 cross 2 matrix, and then you will have a column vector having two components, 0. Then the last row is left out in this 3 cross 3 matrix. That will be L and then L33, where this vector L and the real number L33 are not known to us, but you can get them by equating A3, which is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33 is equal to L3, L3 transpose, right? From there you can get the vector L and L33. And then once you have L3, then define L4 similarly and obtain that L4 by equating A4 equal to L4, L4 transpose, and then you keep going like that. Okay, let us take an example and see how to construct the Cholesky's factorization for that matrix. Let A is equal to 9, 3, minus 2, 3, 2, 3, and minus 2, 3, and 23. You can check that A is positive definite, and also you can directly see that it is symmetric. Therefore, you can apply Cholesky's factorization for A. As I told you, you can construct the Cholesky's factorization step by step. First, take A1, which is equal to 9, and from there, you can get L1 is equal to 3, right? Then define L2 is equal to L1, 0, L21, L22, and that gives me actually 3, 0, L21, L22. And how to get L21 and L22? You consider A22, which is the principal submatrix of order 2 from A, that is given by 9, 3, 3, and 2, and that you want it to be equal to L2, L2 transpose. That gives you A22, which is 9332 into L2, that is 30, L21, L22 into L2 transpose, which is 3, L21, 0, and L22, right? That is equal to 9, 3 into L21, 3 into L21, L21 square plus L22 square, right? Now equate the elements on both sides. You will have 3 times L21 is equal to 3. That gives me L21 is equal to 1. And similarly, L21 square plus L22 square is equal to 2. And that gives us L22 square is equal to 1, or L22 is 1, right? So we got L2 as 3, 0, 1, 1. Now from here, we will have to go for the next step, where we will take A3 equal to A, because we are given 3 by 3 matrix, and L3 is given by L2, then 0 column vector, and the vector L and L33. What is L? L is nothing but L31, L32, right? And now you have to write A3 is equal to L3, L3 transpose, where A3 is written by 9, 3, minus 2, 3, 2, 3, minus 2, 3, 23 is equal to, on the other side, you have L2, which is 3, 0, 1, 1. Then you have to put the last column as zeros. And finally, you have L31, L32, and L33. That is your L3. And L3 transpose is going to be 3, 1, L31, 0, 1, L32, 0, 0, L33, right? So that is your L3 transpose. Now you do L31, and then the second row, last column, will give me L31 plus L32. And if you compare them on the right hand side, you have the first row, last column is going to be minus 2, and second row, last column is going to be 3, right? And from here, you can observe that I'm precisely solving the L3, L is equal to A, where A is this. That's a lower triangular system, and it is just going with the forward substitution. That's what we are getting. L31 is equal to minus 2 by 3. And when you substitute here, we will have L32 is equal to 3 plus 2 by 3, which is equal to 11 by 3, right? So we got these two elements. Now we have to only get L33. For that, what we will do is last row, last column here will give us L31 square plus L32 square plus L33 square is equal to, correspondingly this side you have 23. Out of this, we know what is L31. It is 2 by 3 minus, therefore it is 4 by 9, plus we also know L32, therefore it is 121 by 9 plus L33 square is equal to 23, and that gives us 125 by 9 plus L33 square is equal to 23, or L33 square is equal to 23 minus 125 by 9, right? That gives us 207 minus 125 by 9, and that is going to be 82 by 9. Therefore, L33 is equal to plus or minus root of 82 divided by 3. You may choose to get plus or minus from here. Let us take plus and write our L3, which is the required lower triangular matrix for our Cholesky's factorization, as 3, 0, 0, 1, 1, 0, and minus 2 by 3, 11 by 3, and root 82 by 3. Okay, all the diagonal elements are positive. You see, if you choose the last element as negative here, then it will not be so. That's the idea. You can check that A is equal to L3 into L3 transpose.